Right, welcome all. We want to have solution to this tutorial problem. We want to learn a few things from the tests. The first test or first question of the test, the instrumentation transducers test. The first question asks us to enumerate two velocity transducers suitable for instrumentation systems. Here we are talking about analog transducers that are applicable for converting velocity into other forms of energy, such as electrical energy. So this is what we are looking at here, and we can mention at least two here that can give us this that we can get the work done with. For instance, we can talk about tachometer. The tachometer is a velocity transducer. Also, we can talk about another device such as the optical encoder. It can also convert velocity into electrical signal. So that is about question one. So we have so many transducers that convert various energy into electrical energy, or even vice versa sometimes. We have various transducers that have been discussed so far. Those are converted energy of various forms, such as potentiometric transducer, capacitive transducer, optical encoder, and so on and so forth. So that is where the question is coming from. Now let's look at the second question. The second question is here. It's talking about logic function that we have on the truth table here. There's a logic function that generated the truth table. So the output x, we are going to write out the sum of products for the output x. Don't forget, we are going to deal with the I at the output, where we have 1 1 1 1 1. Then we look at the sum of products expression of the inputs A, B, C, D that gives us that for each row. Then we are told to also draw the logic diagram for the simplified logic expression. After simplifying this through kind of map, we are now going to draw a logic circuit diagram to represent that. So first of all, we simplify by kind of map. Then after simplifying it, we draw the logic circuit. The logic circuit, combinational logic circuit for that, we draw it out. And the last one, we are going to convert the simplified expression that we obtained from kind of map in the question A here into a product of sum. What the expression we get out will be sum of products. Then we are going to convert it to product of sum. We need De Morgan's theorem to achieve that, and that is what question 2 is all about. So pay attention as we do that on the board. So let us look at the question number 2. We have so this is the way to develop the truth table for 4 input combinational logic gates A, B, C, D. Okay, this is the given truth table. So we are going to look at this and then simplify using a Kernoff map. So we have Kernoff map like this. Okay. So that's what we have. We have the Kernoff map for 4x4 map for 4 input combinational logic gates. So we're going to transfer the I into the map. We're going to map it, into their respective cells. The 0 0, the low, we are not dealing with that. This is a simplification using Kernoff map, whereby we're going to arrive at a sum of products. Okay, so let's see where we're going to transfer the high output into the map, to the cells, mapping them into the cells. follow along with me. We have okay, let's label this one first. A bar, B bar, A bar, B, A B bar. Then also here we have C bar, D bar, C bar, D, C D, then C D bar. So we are going to look at anyone that is 0, it means that letter carries a bar. Anyone that is 1, that letter doesn't carry a bar. Here we have A bar, B bar, C bar, D bar, and this is X bar also. Alright? So where we are dealing with it, we are going to deal with where we have 1, 1, 1, 1, 1, 1, 1, and then map them into the various cells. So we transfer this 1, 1, 1. So we're going to transfer the I into the map. We're going to map it, into their respective cells. The 0, 0, the low, 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 we are not dealing with that. This is a simplification using kind of map, whereby we're going to arrive at a sum of products. Sum of products. Okay, so let's see the way we are going to transfer the high outputs into the map, into the cells, mapping them into the cells. You follow along with me. We have okay, let's label this one first. A bar, B bar, A bar, B, A B bar. Then also here we have C bar, D bar, C bar, D, C D, then C D bar. So we are going to look at anyone that is 0, it means that letter carries a bar. Anyone that is 1, that letter doesn't carry a bar. Here we have A bar, B bar, C bar, D bar, and this is X bar also. Alright? So where we are dealing with it, we are going to deal with where we have 1, 1, 1, 1, 1, 1, 1, and then map them into the various cells where they belong. Looking at this one, for instance, you have A bar, B bar, C, D bar, A bar, B bar, C, D bar. So we are putting 1 here. The next one, A bar, B bar, C, D, A bar, B bar, C, D. We are putting 1 here. The next one, A bar, B, C, D, A bar, B, C, D here. The next one, A, B bar, C bar, D, A, B bar, C bar, D. So it is here. And then we have this one, A, B, C bar, D bar, A, B, C bar, D bar. So they are meeting here. Next one, A, B, C bar, D, A, B, C bar, D. So it's here. And then the last one, A, B, C, D. Okay, A, B, C, D. A, B, C, D. Put 1 here. To map now, we map in powers of 2, 2 raised power 1, 2 raised power 2, 2 raised power 3. So we can see, so we look for the highest power of 2, 2 raised power 3, 2 raised power 2. You can see number of 1 that's that are sitting together by each other, close to each other, map like that. You can see 8, then we can see 4, 5. You can see 4, then you look for 2. So we map these together, for instance. We won't map these 2 because if you map these 2, then we are going to map these 2 again. That will be mapping. So we can actually map this. And we can actually map this. And we can map this. Okay, that is the proper mapping for this. We cannot map this again. because we have already mapped it here. And we have mapped this one also here and here. So that is correct mapping. So we can now write the expression for the x. That is it. Okay. X equals a bar c plus b bcd plus abc bar c bar plus a bar c bar d plus a bar c bar d. So we're going to draw the combinational logic circuit for this. We're going to require A and A bar, B and B bar, C and C bar also, but only D. So we can do it this way. We can put A bar here. Same thing for B. This is A, then there will be A bar here. Same thing for C. This is C, then there will be C bar. So to draw A bar B bar plus C, sorry, A bar B bar C, we can have, this is an AND gate that includes these three, another AND gate for this, another AND gate for this, and another AND gate for this. So we do AND gates. First AND gate, A bar B bar goes in, B bar goes in, plus C. C goes in from here. There's no C bar here. Then we have BCD, okay? Another AND gate for that. BCD, okay? There's a dot here. When there is no dot, there is no connection. They are not connected, okay? C can go in like this. D can go in and remain C. Remain B. So we can bring B from here. That's it. These wires are across here, they are not connected. Okay. Then the next one, A, B, C bar, another AND gate. A, B, C bar, we can bring A down from somewhere. Let me use this place. A, then B, then C bar. Is coming from here. Alright. These ones are just crossed, they are not connected. The wire crossed. When they are crossed, they are connected, there is a dot there at the point of connection. Okay. Then A bar C bar D, another one. A bar C bar D. We have A bar from here. Cross it from here. A bar. We have C bar is here already, so we can tap it from here. C bar and D. So D is just coming from here. So we have 4 AND gates. The 4 AND gates will now enter into one OR gate. OR gate, and that's why they call it sum of products, because the final gate is actually an OR gate. Okay, so we bring the outputs of the 4 of them into the OR gates directly. And that is it. That is the conditional logic gate for the simplified expression for that truth table. Alright, so that's question number B. Then question number C. Question number C requires that we convert this sum of products into a product of sum. Okay? Into a product of sum. Alright. So we need to actually rub this off. Rubbing this off to actually do the conversion from a sum of products to product of sum. Conversion from sum of products to product of sum. Okay? So we apply De Morgan's theorem. De Morgan's theorem. Okay. So let's look at that. So the idea is to put a bar on both sides. But when you put a bar, you have to put another bar again. So double bar. So we're having this. This is double bar on the left hand side, double bar on the right hand side. A bar, B bar C plus B C D plus A B C bar plus A bar C bar D. So we have the double bar. Now the double bar means there is no bar. Bar means the bar is cancelled. So now we have X bar here. X bar remains X. So we're going to use the double bar here to apply the Morgan's theorem to the right hand side of the expression. So we have first bar remaining. Then we are going to apply the Morgan's theorem now. A bar, B bar C bar. So when we apply the Morgan's theorem, the OR gate changes to hand here. BCD, another one again, AB, C bar, and there is one bar also. The lower bar breaks onto the AND gates and turning the OR sign into hand. That's why I'm changing this to brackets. A bar, C bar, D, another bar here. So we continue to apply the Morgan's theorem to the AND gate also. We have the longer bar remaining. We have A bar, and the sign changes to plus. B bar plus C bar, and then brackets here. B bar plus C bar plus D bar, then A bar plus B bar plus C bar, and then A bar plus C bar plus D bar, and then the longer bar remains. So we close the brackets here. So right now we have converted this sum of product to product of sum. So we can write the last one as x equals A bar is now A plus B bar is now B, then plus C bar. Then change this one to B bar plus C bar plus D bar to A bar plus B bar plus C to A plus C plus D bar. That is the final expression. So this is the product of sum. You can now see that we have products, bracket, that's like multiplication, and what is inside each of them is sum. Sum here means that we have OR gates inside this bracket, 3 input OR gates, 3 input OR gates, another 3 input OR gates, another 3 input OR gates. But all of them will enter into one final AND gate, not AND now, NAND, because of this bar. The gate will now be NAND, not AND. And so we have converted this sum of products into product of sum. So the Morgan's theorem helps us to effectively convert the sum of products to a product of sum, as we have on the board here. And so that is the solution to question number 2, A and B. Solution to question number 2, A and B. So we have seen that. Now the last part will be question number 3, that is a calculation based on the thermistor. So we are looking at the thermistor calculation now. Let's look at that. So don't forget to give us a thumbs up with this video, like and share. If you haven't subscribed, please subscribe to the channel. So we are moving on to the calculation now. So let's look at the last question. The last question is a calculation based on another transducer, which is a thermistor. Thermistor is a transducer that converts heat energy into electrical energy. converts heat energy to electrical energy. So we have a formula that we are going to use to calculate that is known to you all. So we're going to do that. We're going to work it out on the board now, so that everybody will see clearly what the solution is, how to apply that formula to get the answer. So let's follow as we do this calculation. This one is based on thermistor converting energy, that is when it's at a reference temperature in degrees Celsius, and then it's going to measure temperature at another level, higher level. So what is the resistance of the transistor at this point? That's what we are going to calculate. So that is it. So follow along as you do it on this board now. Formula of interest to number 3, that solution to number 3 is RT equals RO exponential B into 1 over T minus 1 over TO. Okay, and T is actually 105 plus 273. That gives us 378 Kelvin. So the temperature must be converted to Kelvin, and then TO equals 20, that is reference temperature, plus a 273, and that's 293 Kelvin. Okay, so we can now substitute this into this formula. Therefore, RT equals RO. Reference temperature is RO, that's 105. Reference resistance at reference temperature, that is 105 ohms. So you can now have 105 E raised to power 2315, beta is given as 2315 into 1 over 378, 1 over 378 minus 1 over 293. Okay, and that gives us 105 E raised to power minus 0.00. You simplify all of this, we have 0.007674. Okay, multiply by 2315, that is this. So that gives us 105 E raised to power minus 1.7765. If you simplify using your calculator, you get 17.77 ohms. And that's the answer to the problem, 17.77 ohms. So that is it. You can see how simple it is to apply that formula. You have to be careful. You must convert given temperatures into Kelvin. Very important. Also, punching your calculator on this fraction, you must be careful not to make a mistake to arrive at the correct value, which is actually a negative number. It's a negative number. Alright. So when you simplify this, you get this negative power of the E. So when you simplify finally, you get 17.77 volts. That is it. So if you have any question, please put your question down on the comment section. I will personally respond to your question. Now, if you haven't done so, smash the notification bell in order to be notified any other time I'm bringing interesting videos like this. Don't forget to give us a thumbs up for the video and share to your friends. Until another time, bye.